Hey guys, welcome back. Welcome to Vedantu's J channel. I'm sure you all are watching this video to do a quick revision of all the formulas with respect to your board examination of physics. And if you have not, then there has been a video done before this as well, which includes the formula list from electrostatics, Gauss's law, capacitance, and current electricity. Okay guys, so I'm back again, and in this video guys, what are we covering? We are covering magnetism, EMI and AC. When I say magnetism, obviously we'll be speaking about moving charge, we will be speaking about magnetic field due to current carrying conductor, and we'll be speaking about bar magnetism as well. Okay guys, so for all of you who are not aware about me, who do not know me, this is me, your Suri Sir, also known as Mogambo on this channel, because when you'll be cracking any of the examination, Mogambo khush hoga. Okay, cool guys, a quick overview about the entire 12th standard physics. So you have electrostatics, Gauss's law, capacitance, current electricity, magnetism, MEEC, which is magnetic effects of electric current, bar magnetism, EMI, AC, wave optics, ray optics, and modern physics. You can see that things which are marked in black color are the topics or the chapters that we are going to cover the formulas of in this particular video. Okay, so do not worry, I'll be taking you through all the important formulas of the chapters which I'm mentioning here. I'm not getting into the derivation because yes, you want to do a quick revision. That's what basically is the objective of this video. Okay, so guys, if you are interested in studying any of this chapter very much in detail, then I have a solution for that as well, and that is Vedantu's micro course. And right now an amazing deal is going on, and that is any of the micro courses from any of the subject, any chapter that you want to study at your own speed is available for you for just ₹1. How can you enroll for a micro course? Link for that is available in the description of this video. All you have to do is click over there and enroll for any of the courses and study at your speed, at your convenience. Cool guys, so let's go forward without wasting any further time. We have the very first chapter, that is magnetism. Okay, so guys, first thing first, if we speak about charge which is not stationary anymore. In the case of electrostatic, charge was stationary, charges were not moving, but now when the charge starts to move, it starts exhibiting the magnetic phenomena. Okay, so now if I speak about the amount of force which is experienced by a charged particle whenever it is moving, if there is a possibility of a magnetic field and electric field simultaneously being present, that is when we say that the net force which is experienced by the charged particle is known as the Lorentz force. How we calculate that? That force is given as QE, which is the electrostatic force, we are aware about that, and QV cross B. So V cross B is basically the cross product of the charge velocity and the magnetic field. Okay, now if we speak about what happens to a charged particle when it is moving perpendicular to the direction of magnetic field, you can see that the charged particle has a velocity in this plane and the magnetic field is going inside, so it starts to move in a circular path. You can calculate that by using right hand palm rule as well. So the value of the radius of the circular path is given as mv upon qb. You can find that very easily by equating qvb equal to mv square by r, which is the centripetal force. You get the value of the value of the radius of the circular path, that is mv upon qb. And because it is moving in a circular path and no change in the velocity because there is no acceleration possible, so the value of the time period comes out to be 2 pi m upon qb. How do I calculate the time period? That is nothing but the overall circumference 2 pi r divided by the speed with which it is moving. So you can put the value of r from here and you can calculate the formula as well. You can find out the formula as well. Okay, so don't worry about that. If I speak about a force on a current carrying wire, so if you have a current carrying wire which is placed in an external magnetic field, then the force which is experienced by the conducting wire, first of all, why is it going to experience it? Is because a conducting wire which has some current flowing through it will have charges flowing through it, and whenever a charge is flowing in a magnetic field, it will experience the force QV cross B. So if we find out the formula for that force, it is given as IL cross B. Okay, where L is the direction of length, we are considering it to be a vector, which is along the direction of the flow of current. Okay, and if we talk about something called as magnetic moment, later on in bar magnetism also, you know that a bar magnet is basically a dipole, so a current carrying loop also behaves like a dipole. If you have an area vector which is perpendicular to the direction of the plane of the loop, then we calculate the value of magnetic moment, which is given as mu vector, given as I into area vector. Okay. Sometimes you also find the magnetic moment being represented as capital M, so do not get confused there. Mu will also be representing another quantity in the same chapter known as the permeability, so don't get confused. Mu is basically, here it is representing magnetic moment. Okay, and moving on from here, now comes the part where we try to calculate the magnetic field due to the current carrying objects. So if you speak about a general element current carrying wire, or having any shape, any size, then you have an element of that conducting wire which is given as length dl, and at a distance r from it, making an angle theta, the position vector is given by r vector. The magnetic field will be found by using your right hand thumb rule. So we calculate the value of the magnetic field, small magnetic field due to the small element, by the formula which is written as mu naught upon 4 pi, okay, whose value is 10 to the power minus 7. So mu naught upon 4 pi I dl cross r by r cube. It can also be written in terms of magnitude as mu naught upon 4 pi I dl sine theta by r cube, where r is the distance between the element and the point where you are interested in calculating the magnetic field. Okay. Apart from that, if you have a finitely long conductor, so have a look at the diagram properly, guys. Usually the diagram that you see has both the angles of the inside of the triangle which is being formed. So from the conducting wire whose current inside it is given as I, at a distance d perpendicular to it, if there is this point where we are interested in calculating the value of magnetic field, have a look at this angle theta. It's outside, exterior angle it is. So the formula is given as mu naught I upon 4 pi d cos theta 1 minus cos theta 2. So no problem if you know the other formula. Remember that in that case theta 2 is the angle which is an interior angle. Then the formula becomes mu naught I upon 4 pi d cos theta 1 plus cos theta 2. Okay guys, so this angle is an exterior angle, that's why minus cos theta 2 is coming over there. Okay, if we speak about the the magnetic field due to an infinitely long straight wire, this was a finitely long, so if you want to find out the magnetic field due to an infinitely long straight wire, then the formula becomes mu naught I upon 2 pi d. Okay, that simply means what, guys? The values of theta 1 and theta 2 will give you the value as 2. So theta 1 will be 0 degree, theta 2 will be 180 degree. So cos 180 will be minus 1. So 1 and minus of minus 1 will give you 2. One of that 2 value will cancel 4 by 2 times. So that's why mu naught I upon 2 pi d will be your formula. If you have two infinitely long current carrying wire carrying current I1 and I2 placed at a distance d, then they try to attract each other by a force whose value per unit length is calculated as mu naught I1 I2 upon 2 pi d. So basically you are calculating the value of magnetic field due to one of the wire, which is mu naught I upon 2 pi d. You are taking its multiplication by using the formula F equal to IL cross B. Okay, cool. Now instead of having a straight wire, if you start having a arc whose angle subtension at the point where we are interested in calculating the magnetic field by using again the right hand thumb rule, but this time your fingers are curled along the direction of the current and thumb is giving you the direction of the magnetic field. So it is an anti-clockwise current, so magnetic field is coming towards you. If it will be a clockwise current, magnetic field will go inside. So the general formula is mu naught I theta upon 4 pi a, or you can also write it as mu naught I upon 2a theta upon 2 pi. Okay, so any of the formula you can remember, and if the theta value becomes 2 pi, then you will have a complete circular ring carrying current. So the value of the magnetic field at the center of that circular wire carrying current I will be mu naught I upon 2a, where a is the radius of the circular section. Okay. Apart from that, very similar to Gauss's law, here we study something called as Ampere's law, and here we have the conducting wires being enclosed in a ring, or in, you can say, a loop, which we call as the Ampere's loop. So that is why there is a closed integral. So closed integral B dot dl is equal to mu naught into the enclosed current in that Ampere's loop. Okay. Using that only we find out the value of the magnetic field due to solenoid, and a solenoid is basically like a circular ring which has n number of turns being created. For that, the magnetic field is given as mu naught Ni, where N is the number or turn density, you can say. So it is number of turns per unit length. Okay. Similarly, if you have a solenoid which is in the form of a ring, that means if you have created a circular cross section for the solenoid, then we start calling this type of arrangement whose radius is r, we start calling it as a toroid. So for a toroid, the value of magnetic field inside the axis of the toroid, there will be no magnetic field outside the solenoid and outside the toroid also. So in this region and outside region, there is no magnetic field. Magnetic field is only inside the core of a solenoid or a toroid. So that value is given as mu naught Ni upon 2 pi r, where N is the total number of turns, capital N it is, and r is the radius of this toroid. Okay guys, cool. Now if we speak about bar magnetism, that means what? Now you will have physical materials which are just like the normal magnets that you might have seen. Okay, so those magnetism, if you study, we speak about a bar magnet having a south pole and a north pole, and we want to talk about the magnetic field due to this bar magnet on the axis as well as on its equatorial position. So axis is basically along the length of the bar magnet. So at a distance d, if we are calculating the magnetic field B1, so the magnitude value of the magnetic field comes out to be very similar to what we have studied for the electric dipole. This time it comes out to be 2km by d cube. It used to be 2kp by d cube or r cube for the electric field. So here the magnetic field comes out to be mu naught upon 4 pi 2m by d cube. Now what is this capital M? It is nothing but your magnetic moment only. Okay, and B2, which is basically your equatorial position. So at any point which is at a distance d, that value comes out to be km by d cube only. That means what? Mu naught upon 4 pi m by d cube. Okay, if you want to find out the net value of that magnetic field, then you can take the resultant of both of them as well. Okay, now if we speak with respect to Earth's magnetism, we, for our understanding, assume that Earth's magnetism can be studied and compared with a bar magnet, assuming that Earth has a bar magnet inside it, which is creating the magnetism on Earth's surface and nearby area. So if we at any point on Earth say that have a magnetic field of Earth as B, and we resolve it as per the surface of the Earth, then BH is basically the horizontal component of the Earth's magnetic field, and BV is basically the vertical component of the magnetic field of Earth. Okay, so how do we define the angle of dip? Angle of dip is basically the angle which is there between the magnetic field of Earth at any point with the horizontal direction. So that is why the value of BH is basically the horizontal component. So obviously B cos delta. So delta is your angle of dip. Okay. Similarly, there is a device which we use to find out the value of Earth's horizontal component of magnetic field. So the value of BH tan theta can be found as mu naught Ni upon 2r. As you can see, it is a solenoid which is involved over there. So that's why it is mu naught Ni upon 2r, where N is again the turn density, and the current sensitivity, if we speak about, is given as K tan theta. Similarly, if you speak with respect to moving coil galvanometer, then for that also the sensitivity is NIAB, where N is the number of turns, I is your current flowing in it, A is the area of cross section of the coil, and B is the magnetic field, is equal to K into theta. K theta tells you the sensitivity of the galvanometer. Okay, so the total current which is being measured by the galvanometer is given by this particular formula. Apart from that, if you have a bar magnet which is being hanging and it is experiencing some torque in the external magnetic field, then the value of the time period of its oscillation, if it starts to oscillate, is given by 2 pi under root I by capital M into BH. This is a bar magnet, or you can say a magnetometer also, which is experiencing a torque due to external magnetic field of Earth. That value, what you see in this formula, has I as the moment of inertia of the bar magnet, capital M being its magnetic moment, and BH is the horizontal component of Earth's magnetic field. Okay, okay guys, next one. Now we are moving to, from our magnetism chapter, we are moving to electromagnetic induction, which I'm sure you guys are aware about the process in which we try to generate the electricity, and that happens whenever there is a conducting coil or a loop and there is a magnetic source. If there is a relative motion between these two, there will be generation of electricity. Okay, so for that obviously we need to understand magnetic flux exactly on the same lines as we have studied the electric flux. So magnetic flux is just like that, equal to the dot product of magnetic field and the area vector of the loop. And to find out the magnetic flux, you can also do the integration if the magnetic field is not uniform. Okay, then comes the core of the discussion of this chapter, that is Faraday's law of electromagnetic induction, which says that the EMF induced in a current carrying loop because of the change in flux is given as minus d phi by dt, where phi is the magnetic flux. Okay, then comes the Lenz's law. I'm sure you guys are aware about that. This Lenz law only explains the negative sign over there. What does it say? That if there is a change in flux happening through a coil, then Lenz law says that the induced current create a magnetic field that will oppose the change in the magnetic flux. Which means what? If the flux through the loop is increasing, so the induced current direction will be such that it will try to create its own magnetic field and flux, which will try to compensate for the change. If the flux is increasing through it, it will try to decrease it. If it is decreasing, it will try to increase it. Okay, hence the negative sign over there, or minus has been written over there. Okay, if you have a conductor which is moving in an external magnetic field, then it starts behaving like a power source, and the EMF which is generated in the conductor, which we call as the motional EMF, I like to call it emotional. Okay, so that is given by E equal to B into L into V, where B is the external magnetic field in which the conductor is moving, V is the velocity with which it is moving, and L is the length of the conductor. Okay, apart from that, you have heard about the self-inductance phenomena, where you have a coil through which already a current is flowing, but that current, if it starts to change with time, usually happens with the case of alternating current, then the flux that is linked by itself, means the magnetic field lines of the coil which is linked with itself, if it starts to change the magnetic flux, then there is an induced current in the same coil, which we call as the phenomena of self-induction. So the value of flux through the coil is given by L into I, or rather you can say it is directly proportional to the current which is linked with it. More be the current, more be the flux, because more will be the magnetic field, and more be the value of I, more be the value of phi. If you remove the proportionality, we bring a constant called as the coefficient of self-inductance. And to calculate the value of induced EMF, all you have to do is differentiate this phi by using the Faraday's law. So it becomes minus L di by dt. How do you calculate the value of self-inductance for a solenoid? If you can, please remember this value. It is mu naught n square pi r square L, where n is the number of turns per unit length, L is the length, and pi r square is the area of cross section of the solenoid. Okay. Next one, again an important formula, energy stored in an inductor. So far we have seen the energy which is stored in the capacitor, that used to be half CV square. Here the energy stored in an inductor is given as half Li square, where L is the value of coefficient of self-inductance. Okay. If you remember, in the chapter of electrostatics, I told you about the energy density of electric field. Here we have energy density of magnetic field. So that is also energy per unit volume. Remember this formula also, because it is helpful in electromagnetic waves. So it is given as B square by 2 mu naught. There it used to be half epsilon naught E square. Okay. And the mutual inductance is the phenomena which is very similar to the self-inductance, but this time you will have two coils which are placed in the close vicinity of each other. One of them has current flowing through it, other one has no current flowing through it. So whenever we can call the first one which has current as the primary coil, the one which does not have any current already existing as the secondary coil. So any current change in the primary coil will change the magnetic field of it, will change the magnetic flux of it, and the magnetic flux which is linked with the secondary coil, if it is changing, then what happens? Phenomena of phenomena of mutual inductance happen, or you can say the electromagnetic induction happens. So very similar to that, only you can see that flux length of primary with secondary coil is directly proportional to the current of the primary coil. So if you remove that proportionality, we bring a constant called as coefficient of mutual inductance, and take this, put it as per the Faraday's law, which is minus d phi by dt. You get the value of induced EMF in the secondary coil as minus mdi by dt. Okay, and also the EMF which is induced in a rotating coil, which also becomes the basic principle of an electrical generator. How do we generate the AC in a generator? This is basically how we generate that. It is given as NBA omega sine omega t, because the value of angle between magnetic field and area to calculate the flux, that angle is changing continuously because we are making the coil rotate in the magnetic field. So that is why on differentiating that magnetic flux, B into A into sine omega t, cos omega t. So when you differentiate that, it comes out to be B into A into omega sine omega t, and N is the total number of turns. Okay, the first 4 terms that you see, N, B, A, omega, is the maximum value of the AC EMF being generated. Okay, cool guys. Now comes the alternating current chapter. There we speak about how the current gets generated first, which I have already spoken about in the previous slide also. So the value of the current is going to change sinusoidally with time. So that is given by I naught sine omega t plus phi. The value of the time period is 2 pi by omega, where omega is going to be related with the frequency only. And if we try to calculate the average value of the AC current, this one is not that one, but if you have positive cycle and the negative cycle, then the value of the positive cycle current and the negative cycle current average value will come out to be 0, which you can also derive by using the expression which is written over here. But important is to remember that over a complete cycle, the value of the average AC current is equal to 0. But if you try to find out the RMS current for doing the calculation of the heat dissipation, then the RMS value is equal to I naught by root 2, where I naught is the peak value of the current. Okay, how do you calculate the energy? As I told you, RMS value is important for that. It is given as I square RMS times RT. Okay, or simply I square RT it is. So remember that RMS value is important to calculate the value of the energy dissipated or heat dissipated across a resistor of the AC current which is flowing through it. Okay, next, if you start making your AC current flow through devices other than resistor, then the capacitor and inductor are the 2 devices which you can have in the circuit. Capacitor will show some resistance towards the flow of alternating current, which is given by 1 upon omega c. Inductor will also show its own resistance towards the flow of electric current AC, called as the inductive reactance, given by omega L. C, as you know, is capacitance, L is your value of self-inductance. Okay, so overall value of the impedance, which is the net value of the resistance which is being shown or offered by all the elements put together in a circuit. This could be a combination of any of the 3, R, L or C. So the impedance is just like resistance. So what is written over here is nothing but Ohm's law. That tells you it is basically the ratio of EMF to the current peak value. Okay. Now guys, if you take a circuit which has a resistance and a capacitor connected to an AC source, then remember this is called as the Phasor diagram to calculate the value of the impedance. This is how the resistance is. There is no phase difference between the current and the EMF in purely resistive circuit. But in the case of capacitor, the current will lead the EMF. That's why it is drawn over here by a phase of pi by 2 ahead. So this is your resistance of a resistor, this is resistance of a capacitor, 1 upon omega c, and the resultant of both of them is your inductance, the impedance. So the value of the impedance is calculated as under root of R square plus XC square, which is 1 upon omega c. Okay, and what you see here is basically the phase difference between current and EMF when you have 2 elements of R and C present in the circuit. How do you calculate that? You know how to calculate this. This is tan phi is XC by R by using this right angle triangle. Similar thing you will use for an LR circuit. So this time you have an inductor and a resistor being connected. But if you look at the phasor diagram here guys, this is resistance and an inductor. The current lags the EMF by a phase of pi by 2, but their resultant of R and omega L is still the impedance, and this is the phasor value phi. So you can see that the impedance is still calculated as under root of R square plus XL square this time, and tan phi is nothing but XL by R, simply by using this right angle triangle, any of these 2. Okay guys, moving on, if we speak about the LCR series circuit where all the 3 elements are being present, then you can see this is R, this is XC, this is XL, depending upon whose value is more. Their net value will be either XC by XL, XC minus XL like this, or will be XL minus XC. So depending upon whose value is more. Okay, so you'll be able to calculate the value of the net impedance as under root of R square plus XC minus XL square or XL minus XC square. If I want to calculate the value of tan phi this time, then this side divided by this side means opposite upon adjacent. That's how I can find out the value of phase difference between current and the voltage. If I speak about the case when XC and XL are equal, which we call as the phenomena or condition of resonance, then you can equate them. 1 upon omega c, if you equate with omega L, omega comes out to be equal to 1 upon under root LC, or the resonance phenomena whose frequency is given as 1 upon 2 pi under root of LC. Okay. Apart from that, if we speak about the power that is dissipated over here, so power is only dissipated by resistor, it is not dissipated by capacitor or inductor. So the value, you have to remember the expression, is given as E RMS I RMS cos of phi, where cos phi is called as the power factor. Okay, because the value of cos phi for capacitor will be 0 because phase difference of 90 degrees there. For inductor also that will be 0 because there is also the phase difference of pi by 2 being there. Okay, and if you start writing E RMS as E naught by root 2, I RMS as I naught by root 2, so the formula can also be written as 1 upon 2 E naught I naught into cos of phi. Okay guys, now the device whose usually construction, working and explanation comes as 4 marks questions usually in your board examination, so you have to have a good understanding of the primary and the secondary circuit. This one is the primary circuit where there is already some current being generated and will be transferred from the power plant to a township. So this is E1, the primary EMF. N1 is the total number of turns in the primary coil. I1 is the current in the primary coil. The second part, what you see in the diagram, is the secondary coil, which has E2 as the EMF, N2 as the number of turns, I2 as the secondary current. So what you have to remember is that ratio of number of turns is equal to the ratio of EMF of both the coils over here. So N1 by N2 is equal to E1 by E2 and is equal to I2 by I1. That is why you can see the ratio of E1 by E2 is equal to I2 by I1. So how do you remember that? N1 by N2 is equal to E1 by E2 is equal to I2 by I1. Okay, this is basically the amount of power which for an ideal transformer we are assuming the power which is over here is getting completely transferred. So an ideal situation, 100% efficiency is what we are assuming here. Okay guys, cool. So this brings us to the conclusion of this particular video, where we have discussed all the important points and more importantly the formulas which are related to entire unit of magnetism, EMI and AC. Okay, what you see in the background are basically the last year amazing results of Vedantu. Let me just take you through that. It may serve as the source of inspiration for all of you guys. Well, at Vedantu last year in CBSE 12 standard, we had 42% scoring 90% plus marks. Not only that, in 10 standard CBSE, we had 42% people scoring 90 plus marks there as well. More than that, we had ICSE students of 10 standard who scored 55% of those people about 90% marks. 55% people scored, students scored more than 90% marks over there. And not just that, there are scholastic exams like KVPY and RMO, where we had 7 fellowships from KVPY and 25% selection in the pre-RMO examination. Okay guys, well, I hope you guys are taking advantage of this video. If you are liking it, do hit that like button. Definitely share this with your friends. Let them also study along with you. And if you have not so far, do subscribe to the channel and stay tuned. I'm coming back with the third video where we'll be finishing all the remaining chapters, which are obviously optics and modern physics. Cool guys. Till then, keep studying, keep enjoying. See you soon. Bye-bye.